Good morning, everyone. Here's a blower fan assembly, and it is constructed by Eaton. Now the blower fan assembly, the motor stopped working. Here's the original. We replaced out this motor and fan assembly into its housing. Here's the bad one right here. It don't want to. The motor don't want to run anymore. So to control the blower assembly, we have this drive board right here. And in order to power up the drive board, I've got a variac, bridge rectifier, and bus capacitors to apply 300 volts DC to the, let's get it out right here. There's my drawings. I had to map the circuit out. But the X2 connector right here, and I'll put these up at the end of the video so that you can look at those. But on the X2 connector, pin 1 is bus ground, and pin 3 is bus plus. And you have this series of high resistance capacitors right here. 184 kilo ohms, 184 kilo ohms, 184 kilo ohms, 184 kilo ohms. To enable the blower motor to run, we have to apply 15 volts to the XA connector, right here, pin 2, and then pull pin 3 to ground of that 15 volt power supply. We're creating our plus 15 volts for the enable signal from this power supply right here. There's a transformer right here that takes the output of this card into a 1-to-1 transformer right here, and the output of the transformer is applied to the blower motor. Well, let's go. All right. We've applied our 300 volt DC to the X3 connector. You can see some LEDs down here. If the red and green LED are on steady, that means that that control board is in standby. I've got a switch right here to enable the output. The green LED is flashing. That means that you have an output to the blower motor. Gets up and goes pretty good, doesn't it? You see how it ramped up? Okay. I'm going to disable the output. And we're slowing down. Ramps down pretty good. That's nice. That is very nice. I put that yellow piece of electrical tape on there so you can see the motor's blower spinning. Look at that. It takes forever to ramp down, doesn't it? Well, she's working. She's doing real good. We can send this back to the customer. But this is why they sent it to us. That motor and blower assembly stopped working. All right, all. I hope you're having a good day. We're not doing too bad here. We're still fixing things. And sometimes it's good to test the things that you're working on. But if you don't have no documentation on the thing you're working on, you have to draw the circuits out so that like this, for instance. We had to know how to turn this drive on, and in order to do so, we had to map out the inputs and the outputs of that X8 connector. And in order to figure out whether we can put high voltage on this little connector right here, it's always a scary thing to do. But in order to feel good about applying 300 volts DC to this little connector, I mapped this out, and I saw those 4 high ohmic resistors right there. They're surface mount, but they're high enough to where I said, yeah, I can do that. I can put 300 volts DC, a positive 300 volts DC here, and a negative bus ground, a negative of the bridge rectifier on pin 1. Just to alleviate my worries, because it's unusual to put a 300 volt DC voltage on one of these types of connectors right here. But it worked. Now what I did was, I have my meter connected on the plus and bus ground of the bus capacitors, the bridge rectifier, and while I was watching the meter and watching those LEDs, I snuck up on that 300 volts DC. And when those LEDs turned on, I stopped. I said, okay, I made it there. It's not an easy thing to do. You're always worried about destroying something that doesn't belong to you. I mean, right now it was a bad blower fan motor, but if I hooked up the 300 volts DC wrong to this control board right here, it would be very, very hard to fix. And it would be very, very hard to explain to your customer why there's a smoking hole in the middle of the board that wasn't there when they sent it to us. So I get scared about those things. I really do. Anyways, enough of me yammering on like that. But you'll see some of the reasons why I use a variac and a bridge rectifier and a bus capacitor to sneak up on things. And that way I don't destroy something that doesn't belong to me. Oh well, there you go. That's part of my electronic philosophy that you got to hear. Have a good day, all. We'll see you in the next video. Here's the documentation, the pinouts for the blower assembly. Now, when we got this documentation, it didn't tell us what this voltage was supposed to be. So I mapped into the X2 connector to feel good about me sneaking up on this this voltage right here with the variac, bridge rectifier, and bus power supplies. Here on pin 1 of the X2 connector is bus ground. So I applied the ground of that bridge rectifier and bus capacitors to this pin right here. Here we snuck up on pin 3 of the X2 connector until we reached just a hair of 300 volts DC, maybe a little bit more. And we saw the red and green LED turn on. Now down here, I did not know who the inputs and the outputs were of this connector. So I mapped that circuit out and found that pin 2 is the common plus 15 volt DC for the outputs and the inputs. And down here on pin 5, we have that external power supply of plus 15 volts DC and ground down here on pin 5. Now, to enable that fan to run, I pulled the fan control signal, and we'll see in a minute, to the 15 volt DC ground of that external power supply. And that fan got up and ran. Let's go over there and we'll take a look at these inputs. Here are the two inputs on the XA connector. Pin 1 is fan pulse width modulation. I did not apply an input to this optocoupler. All I had to do was pull pin 3 to ground of the external 15 volt DC power supply, and that turned on this LED inside that optocoupler. Now, I could not figure out what the part numbers of these optocouplers were because of conformal coating. The conformal coating was so thick that I could not read the part number on top of the optocouplers. But fan control signal pulled to ground, enabled that blower fan to get up and go. Let's take a look at the second page. Now these are the two outputs. They're alarm outputs, and I don't know what they mean. I mean, does one mean like the fan is not running, the fan is stalled and we're not moving? Not sure what these two alarms mean. But just for the sake of completeness, let's take a look at it. Here's our plus 15 volts DC. That is applied to pin 2 of the external power supply. Here's pin 5. That's applied to this point right here from the external power supply. So this one right here, when that alarm, fan alarm FR10 occurs, pin 7 goes high because we have current flow through the output, collector emitter output of that optocoupler. So pin 7 would go high. Down here, fan alarm FR9 would go low. So pin 4 would be connected to pin 5 through the collector emitter of that output transistor of the optocoupler. Now you have to current limit these. So here we'd have plus 15 volts DC, collector emitter, and then a pull down resistor to pin 5. You could probably get by with 1 kilo ohm, 10 kilo ohm pull down resistor. This point right here would go low with the pull up resistor on pin 4, and it would be pulled to ground. There's your two alarm outputs. So pin 7 would go high and pin 4 would go low. This was, and still is, the confusing part. I don't have it all mapped out, but I was worried about putting 300 volts DC, even though I snuck up on it with the variac and bridge rectifier and bus capacitor. I was worried about applying a high voltage to this point right here. We had DC minus and DC plus. I mapped DC plus into 4 series 184 kilo ohm surface mount resistors. This is the confusing part. This input, as far as I could tell, goes to the gate of this power MOSFET right here. And what I suspect is that we have the high voltage up here through the drain to source of that MOSFET to the switching, the primary of the switching transformer. And the switching transformer's primary is switched by this MOSFET here. The part that confuses me is that's not the way I would have done things. I don't know. You see a lot of strange circuitry in this line of work. I just would not have done it that way. But that's the way it is. If I had the complete schematic, it might make more sense in my brain, but this is all I've got. It was really, really hard just to map this part out right here because of the conformal coating, the protective coating of that circuit. Made it very, very hard to get on anything to find out where it goes. But there it is. That's that. Okay. All right. That was a fascinating circuit that we worked right there. I hope y'all bump into things like that in your travels. It makes for an interesting life. All right. I got to go in the backyard and water the herbs and feed the birds. We'll see you in the next one.